Okay, so today we are starting with chapter 5.1. It is all about combining functions. Most of this is going to be fairly easy stuff that we should get through pretty quick. The main thing is going to be at the very end. We cover some new material that might be a little bit more difficult. So last chapter we talked about dividing functions. We did things like, x squared plus 3x plus 2 over x. And you'd have to either, break that down or solve it or whatever. In this chapter, we're going to be talking about doing different functions with, or different operations with functions, so addition, subtraction, multiplication, and division. And all of them are generally easier than division is. Division is kind of the hardest one for the most part. So functions can be added and subtracted, and doing so is easier than it sounds. For instance, we have f plus g of x. So this is the notation for it. You've got the f plus the g in all in parentheses and then of x again. What this is actually equal to, so f plus g of x is basically the same thing as f of x plus g of x. Similarly, if we had f minus g of x, that is equal to f of x minus g of x. And of course, when you have something like this f of x minus g of x, you can just solve for whatever f of x is, subtract g of x. Similarly, if you have g minus f of x, then you're going to have g of x minus f of x. Now, you'll notice that with addition, it doesn't actually matter which way you have these in, right? F plus g of x is the same thing as g plus f of x. The order doesn't matter. But for subtraction, it's definitely going to. And we'll see a similar thing with multiplication and division. When you have multiplications of functions, it doesn't matter what order you do them in. But when you do division, of course, it will, because it determines which one is being divided by which. In both cases, though, we can simplify this to just g of x minus f of x, or in the case of addition, it's f of x plus g of x. So writing it out in this notation is generally, Writing it out in this notation is generally relatively unhelpful. It's easier to just do f of x plus g of x, but this is the notation for the full function. And the same rules will, of course, apply to subtraction as well. So let's look at how we can do this. We can do this, we can add and subtract functions graphically, numerically, and symbolically. So of course, if we're looking at the functions, in this case, f of x equals 2x, g of x equals x squared, we can look at them graphically. I'm going to go ahead and graph this really quick. So it looks something like, whoa, that was terrible. Something like this. For f of x, it's a little off, I know, but close enough. And then it'd be something like that. And then g of x, which is x squared. Let's change the color. Good enough, I guess. Going Christmassy, apparently. I need some points here. So right there. 1. Come up through 4. These are really bad graphs. But anyway, and then we can solve this. So let's say we wanted to solve for, in this case, f plus g of x. What we would do is we would find f of x. Let's say that x equals 2. So we want to solve f plus g of 2. At 2, f of x, which is 2x, is going to equal 4. And funny enough, x squared will also equal 4. So in this case, we'd have f of x equals 4, g of x, or let's go f of 2. Let's actually put this in. So f of 2 equals 4, g of 2 equals 4. So f plus g of 2 equals 8. Right, you're just doing 4 plus 4. That's pretty simple. If we had, let's say, negative 1, right? So at negative 1, we have g of x is equal to 1, and we have f of x is equal to negative 2. So we would have negative 2 plus 1, which is equal to negative 1. And of course, you could do similar things with subtraction. And later we'll get into multiplication and division. Numerically, we can create a table. So in this case, let's say we have x equals 0, 1, 2, 3, 4. Let's say we want to find f plus g of, let's do in this case 4. We don't have 4 on our graph here, At least, actually, yeah, we don't have 4 for either of them, but we can solve them individually. So f of x is just 2x, so we're going to double whatever x is. So we get 0, we get 2, we get 4, we get 6, and we get 8. G of x is equal to x squared, so we can just fill that in. 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. And then since f plus g of x is just equal to f of x plus g of x, we can just add these two columns, column 1, column 2. We can add these together to get this last column. So we'd have 0. In this case, we'd have 3, we'd have 8, we'd have 15, and we would have 24. So f plus g of 4, then, since this is x equals 4, is, I need a different color, this is kind of hard to see, is, of course, 24, which we already did here. Now, solving them symbolically is going to be a bit more complicated, so we're going to look at that on a separate page. Now, you might think that solving them symbolically just involves plugging in the number into each individual function, solving it, and then being done. And while that is technically true, we can also find a symbolic function that effectively acts as a new function that encompasses f plus g of x. So let's start with this one. We're going to call this function here d of x. We're going to do f minus g. That's going to be, let's say, e of x. Generally, you don't use e as a symbol because e is a number, technically, but we're going to ignore that for right now. And then this one will do h of x. So first, if we're solving for d of x, we have f plus g of x. F of x is 2x plus g of x is x squared. So d of x would be equal to 2x plus x squared, which is equal to f plus g of x. In this case, it's super easy, right? We're just adding these functions together. Now we could solve for f plus g of some number. Let's say we pick 3, since we haven't done that one yet. We could just plug in 3 to this. So 2 times 3 plus 3 squared. We'd get 6 plus 9, which is equal to 15. So f plus g of 3 equals 15. Then if we want to solve for e of x, we need to do, that's equal to f minus g of x, which is equal to f of x, which is 2x, minus x squared. So in this case, f minus g of x is equal to 2x minus x squared. We could plug in any number we want. For x, let's say we wanted to find f minus g of, let's say, -2. So we plug in -2 into this function here. We'd have 2 times -2 minus -2 squared. 2 times -2 is -4. Minus -2 squared is 4. So we'd have minus -4 minus 4. That equals negative. So f of x minus g of x is equal to -8 when x is -2. And then for the last one, g minus f. Again, we could do this a long way, but we're just going to go ahead and start it. We just take g of x minus f of x. So we have x squared minus 2x. Pretty plain and simple. G minus f of x. Right, so in this case, it's pretty easy. All we're doing is we're subtracting one function from the other. There's nothing really complicated about that. Now, when we get into multiplying and dividing functions, things get a little bit more complicated, but they're still not too bad. So similar to adding and subtracting functions, we can also multiply and divide functions, and we can solve them graphically, numerically, or symbolically. So let's once again look at these same two functions. We're going to do the same thing. We're going to draw them all out. Again, ignore how awful my lines are. And then this time, let's actually use a color that makes sense. Let's try blue. Okay, close enough. So let's say we wanted to do f times g. Be really careful with your symbols here. We're going to see a symbol in just a little bit that looks similar to a multiplication, but it means something completely different. And then if you use fxg, like if you use x as a times, it's going to look funny. So a lot of times the book will just write them as fg of x, or f times g with the dot, or occasionally, especially on tests, I might have to write it with like a star symbol, f times g. But any of these things basically just mean f of x times g of x. So let's say we want to do f of g of, how about 1? So what we're going to do is we're going to basically, again, same as last time, this is equal to f of x times g of x. So f times g of x is equal to f times g. So we can do f of 1 times g of 1. And in this case, f of 1 is equal to 2. G of 1 is equal to 1. So we have 2 times 1 equals 2. So f times g of 1 is equal to 2. We could also do dividing. We could do f divided by g. So that would look, I'm going to erase the graph, but f divided by g of, let's say, 3, which wouldn't have been on my graph anyway. So if we plug in 3 for f of x, it's going to be 6. G of x would be 3 squared. That's 9. So you'd have 6 divided by 9, which would be 2/3. We could solve this graphically just by finding the actual points. So we'd find what f of 3 is on our graph of f of x, and then we divide it by what g of 3 is. And in this case, that gives us 6 divided by 9, which reduces to 2/3. Numerically, we can create a table, again, much like this. So let's use the functions instead of our graph this time. Let's say we want to do, let's pick different numbers, 2, 3, 4, 5, and 6. Since f of x is just 2 times x, again, we'll just double these numbers, 4, 6, 8, 10, and 12. And then g of x is x squared, so 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. Now, f times g of x is, again, this is equal to f of x times g of x. And luckily, in this case, we've solved already for f of x and g of x. So in this case, we have 16. In this case, we have 54. This one is 128, I think. 250. As you can see, these are getting a little bit out of hand. What is this one, like 432? Something like that. 360 plus 72, yeah, 432. So this would be what f times g of x is. We could also do f divided by g of x for all of these. So for in this case, you would have 4 divided by 4, that'd give you 1. 6 divided by 9, 2/3. 8 divided by 16, that'd be 1/2. 10 divided by 25 would be like 2/5. 12 over 36 is 1/3. And then you could also do g divided by f, which in this case would give you 1, 1.5, 2, 2.5, and then 3. It's kind of interesting, actually, that relationship. But anyway, so multiplying and dividing, again, are not too terribly difficult. But we can also solve these for these functions here. So in this case, symbolically, we've got f times g of x. That's equal to, so here, let's do this. F times little star g of x is equal to f of x times g of x. So in this case, we have 2x times x squared, which is equal to 2x cubed. So f times g of x equals 2x cubed. F divided by g of x, this is equal to f of x over g of x, which is equal to, in this case, 2x over x squared or 2 over x. The x, of course, cancels with the squared on the bottom. And then g divided by f of x is equal to g of x divided by f of x, which in this case would be x squared over 2x or x over 2. So solving them symbolically, again, not necessarily as difficult as it sounds. Of course, when you get more complex functions, like let's say in this case we had an f of x that was x squared plus 3x plus 2, and then let's say we had g of x was equal to 1 over x minus 1, then f times g of x is equal to f of x times g of x, which is x cubed plus 3x plus 2 times 1 over x minus 1, which is equal to x squared plus 3x plus 2 over x minus 1. And you could look at this and hopefully recognize that this is what we were doing a lot last chapter. I wouldn't actually make you solve this in this one. That's not really the point of this chapter at this point. You should be able to tell me right away, though, that 1 is not a possible option. You could not take f times g of 1 just because you couldn't take g of 1. That would be undefined, but that's not really what we're talking about in this chapter. So the last thing that we want to talk about, perhaps the most important thing from this chapter, is composition of two functions. So early on in the year, I first started telling you guys to write things. Where is my pointer? Here, let me change this back to red so we can see it better. I first started telling you guys to write things as f of x instead of y. And I told you that there was a good reason for using f of x. And we are finally getting to the reason for that. And it is for this specific thing, composite functions. So what this notation right here is, this is supposed to be a smaller circle, but there's actually not a symbol for it in PowerPoint at least. But what this function is saying is we're taking f of g of x. So this is kind of a complex thing that you can't really do with a y equals, right? I couldn't say y1 equals, x squared, y2 equals x, and then have you do f of g, or like y1 of y2 of x. That doesn't make any sense. But we can write a notation that's f of g of x, and this is much more like simplistic to solve, I suppose, or it makes more sense. So basically, this notation tells us to solve g of x. So f of g of x tells us to solve g of x, that's what's in parentheses, and then use that answer to solve the function f. So basically, g of x will become your new f. So if we look at an example using f of x equals 2x and g of x equals x squared, we can solve f of g of 3 and g of f of 1. So first, looking at f of g of 3. Start with this one, and then we'll go to the other one. So f of g of 3, we first want to solve the inner function. That's g of x. So we're going to solve g of 3. G of 3. G of 3 equals 3 squared, which equals 9. Then what we have is f of 9, right? F of g of 3. G of 3 is equal to 9, so now we have f of 9. F of 9, all we do is plug that into f of x, which is 2x. So f of x equals 2 times 9 equals 18. So f of g of 3 is equal to 18. All we did was we solved the inner function, and then we used the value we get from that, which is 9, to solve f of x. In this case, we have g of f of 1. This one's in reverse. So in this case, we're going to solve f of 1 first. So f of 1, which is equal to 2 times 1, which is equal to 2. And then we're going to use 2, plug that into g, and then we'll solve and finish that one. So g of 2 is equal to 2 squared, which equals 4. So g of f of 1 is equal to 4. Now we can also do the same thing using the f of g notation, composite functions notation, to solve using graphs and tables, and we'll look at that right here. So this says to use the graphs of f and g to evaluate the composite function f of g of -7. So first things first, we can rewrite this as f of g of -7. It's important to notice that this open circle thing means this notation right here. This is a little bit easier, I think, to understand because it tells you which function is the one you want to solve first. It's the one that's closest, whereas this might look a little bit more complicated. And this is also what I was talking about when I said be careful when you're using a multiplication symbol here, because if you get it mixed up, you might think that we're talking about a composite function when we're just trying to multiply, or vice versa. Anyway, in this case, we want to start with g of x and we want to solve for g of -7. So we go to our graph. We know that y equals g of x is graphed here in red. So in this case, this line is g of x. We're looking for g of -7. -7 is right here. So we go up. G of -7, g -7 is equal to positive, looks like 5, equals 5. So that means that we're now going to take f of 5. Right? We solved g of -7 by finding it on the graph, and now we're going to look for f of 5. So for f of 5, we're going to go over 5 and find it on f of x, which is graphed here in blue. That's right here. Go back over to the left. That is at 4. So f of g of -7 equals 4. Right, so then let's say we wanted to solve for, let's do f of g of 2, and then let's do g of f of, actually, does this even work? Yeah, that should be fine. We'll do g of f of, let's say, 6. So for f of g of 2, first we want to find g of 2. That's going to be here at -4. So g of 2 equals -4. Then we want to find f of -4. So we go to -4, that's here. Go up to our graph of f of x, which is in blue. That's right here at, looks like 7. So this is 7. Then for g of f of 6, this time we're going to start with f because f is our internal function. That's the one closer to the middle. So we go to f of 6, look at 6, we go up. F of 6 is apparently 5. So that means we need to solve g of 5. And g of 5, we move over to 5, which is right here, drop down. And it looks like that is at -7. So g of f of 6 equals -7. Right, like that. So again, it's not too terribly difficult. You're just starting with the inner function, you find the point, and then you use that new point for your outer function. And you can actually do like f of g of f, 2, and like solve this all the way out as well. You can do this. You could have 3 separate functions, all graphed the same, and you could do as many different weird of, f of g of h of q of p of x, and solve all of those out. You just start with whichever one is most internal and then work your way outward. So it's not too terribly difficult. Now, solving composite functions numerically, generally speaking, this is even easier because you will know if you did something wrong by not being able to find the value in your charts. But in this case, we want to solve f of g of 3 and g of f of 3, or of 8. So g of x is this one here, which we can tell because it's labeled right there. And this one is f of x right here. So the first one, we want to start with g of 3, g of 3. So when x is 3, g of x is 14. So g of 3 equals 14. So that means we want to solve f of 14. So we go up to our f of x function, look for 14. F of 14 is equal to 2. So f of g of 3 equals 2. And then since we want to do g of f of 8, we're going to start with f of 8. So f of 8, we look for 8. on our x value for f of x. That gives us 11. So then we want to find g of 11. So we come down here, we look for 11 for our x, that's here, which gives us -3, which means that g of f of 8 equals -3. And we're done. That's all we have to do on those ones. Now, those ones aren't too terribly bad, but solving composite functions symbolically is a little bit more difficult. What we have to do is we have to substitute the entirety of the inside function for the variable in the outer function. So we could do this with our previous ones, but I wanted to do one with a little bit more difficulty. So for example, in this case, we have f of x equals 3x squared plus 2x plus 3. And we have g of x equals 1 over x. That looks like an I. I don't like this font. We can find both f of g of x and g of f of x, and we can do this symbolically. So this way, you'd be able to just plug in any number you want into one formula, and then you'd be done. So f of g of x involves subbing the internal function, that's g of x, in for x wherever you see it in f of x. So f of g of x equals, we're going to take 3 times, now wherever we see x, what we're going to do is plug in g of x, which is 1 over x. So we'd have 1 over x squared plus 2 times 1 over x plus 3. And that's all we have to do. Now we could solve this all out. Probably don't really want to, but basically you'd have 3 over x squared plus 2 over x plus 3. This is equal to f of g of x. So this is a simplified version. All I did was multiply these out, which, isn't too bad. But all you did was take g of x, take this entire function, and plug it in wherever you see x. So remember early on in the year, I told you that if you had like g of x squared, all you're doing is plugging in x squared wherever you see x. So in this case, g of x squared would be 1 over x squared, right? And that's how I explained that g of 2, you just plug in 2 wherever you see x equals 1 over 2, and then you're done. This is the same idea, except now we're plugging in entire functions instead of just some variable or some number. So then if we want to do g of f of x, we're going to start by using the function of g. So we have 1 over, and then since we have an x, we're going to plug in all of f of x, which in this case is 3x squared plus 2x plus 3. Now, one of the things I want to take into account or to have you notice right now is that these are going to give you very different terms. For instance, if we solve f of g of 2, and if we compare that to g of f of 2, these are going to be very, very different answers. And let's look at why. If we plug in 2 to f of g of x, that's our top one, we'd have 3 over 2 squared plus 2 over 2 plus 3. 3 over 2 squared is 3/4. 2 over 2 is 1. 3 doesn't change. So we'd have 1 plus 3, which is 4. 4 and 3/4. So our answer is 4, 3 over 4. 4.75. You can make it 19/4, whatever you feel is easiest. G of f of 2, however, all we're doing is plugging in 2 wherever we see x into this equation. So we'd have 1 over 3 times 2 squared, which is 4. So 3 times 4 is 12, plus 2 times 2, which is 4, plus 3. So basically you have 1 over 19. And you'll notice that these are incredibly different answers. 1 over 19 versus 4 over 3 and 4 and 3/4 are obviously not the same thing. So you make sure that when you see these, you don't get confused. Because again, if we did multiplication, f times g of x, it doesn't matter which order we do them in. But when we do f of g or g of f, those are different things. So make sure you keep those separate. This one, the homework for this assignment won't be too terribly bad, I don't think, but we can always talk about it in class as well. That's all for this section as far as I know. Yeah. that's it for this one. So hopefully this won't be too bad. I'll talk about this in class, but the schedule for the rest of this term, we're going to go through, I think, 4 of the sections this week, and then 2 of the sections next week. We'll have a couple of days before the test, and then we're going to try to finish the test before we go into that last 3-day week. That way, the last 3-day week can be used for makeup or retakes or whatever you need to do to make sure that you're passing the class before we go to winter break. So make sure you stay on top of this one. Make sure you're doing things as they come out. Don't wait and procrastinate on these assignments, because if you're not ready for this last test, then you could end up getting behind and we won't have a whole lot of time to make it up the last week. So please stay on top of things, and good luck, I guess.